Lesson 69, we are going to add and subtract radical expressions. And I want to kind of do a little bit of review about a radical expression. So a radical expression has parts, right? The symbol is called the what? Radical. Right? The number that's on the outside of the radical is called the... It's called the index of the radical. Okay? The index of the radical. It's important. The part that's underneath the radical is called the radicand. Okay? And the reason that we're reviewing this is because we're going to need these definitions to we're going to need these definitions in what we're talking about today. So we can say radicand and you know what I'm talking about. We can say index and you know what we're talking about. Yes?
Is the x like the square and the...
Yeah, so an example of that would be the cube root of 4x squared, something like that. The index of this radical is 3. The radicand is 4x squared. Right? Now, in order to add and subtract radicals, all right, we need to define what like radicals are. And this is an extremely important definition. Like radicals have the same index and the same radicand. So we're establishing what like radicals are. Okay, they have to have the same index and the same radicand. Cube root of 2x, cube root of 2x. Same index, same radical, same radicand. Okay? In order to add or subtract radicals, they must be like radicals. Just like terms. Have to have the same variables with the same exponents. Remember that a index on a radical is an exponent. The square root is the 1/2 power. Cube root is the 1/3 power. So this is the same as like terms. Like radicals have to have the same index and the same radicand. All right? And now the process tells us that if the radicals are like radicals, what does that mean? If they have the same radicand and the same index, then they're added or subtracted just like terms are added or subtracted. Because if they have the same index, then they do have the same exponent. Okay, radicands are the same and index is the same, then that means the exponents are the same and they're like terms, and we can add and subtract radicals like radicals in the same way that we add or subtract like terms. So how do you add like terms? What's the rules for adding like terms? 2x plus 7x. You add the coefficients. Variable stays the same. Whatever you're adding stays the same. So 2x squared plus 7x squared is 9x squared. All right. Same thing with like radicals. You add the coefficients, the number that's in front of the radical, and you keep the variables the same. All right. So let's just look at some examples. 2 square roots of 7 plus 4 square roots of 7.
6 square roots of 7.
6 square roots of 7 is correct, right? Because the radicals are like, same index, same radicand, we can add them. The next one, are those two radical expressions like radicals?
Yes.
Yeah, right? The radicands are both xy. The index is both square root, so we're good to go. What's 4 minus 6? Negative 2 square roots of xy. So you could read that as negative 2 square roots of xy or negative 2 times the square root of xy. Either way. Yeah, we did this in lesson 70. You guys, most of you got those correct, right? We're going to work some today that are a little bit more complicated than that. But all right, what about this one? Why can't you do it? So immediately recognize that these two things aren't the same and we can't change them. Why can't we change the square root of 2 or the square root of 11? They're already simplified, right? They're actually both prime numbers. They don't have any perfect square factors, so we can't do anything to change it to make the radicals the same. So we can't do anything to it. We circle it and move on. Or you could write already simplified. This is like 6x plus 8y. That's simplified. You can't do anything to it. Okay? What about this? Now, this looks complicated, but don't get all wrapped up in how complicated it looks.
That'd just be 5.
We could add the first two. Why can we add the first two, Brooklyn?
Because they have the same, like...
Because they're like radicals, yeah, and the denominators are the same. I love that all the denominators are the same, but this poor one here, it's just, the one that's out there on the end, is just lost, right? It's not like the others, even though it does have a same denominator. We can't do anything with it because the radicals are different. These two have like radicals, so we can add 2 plus 3, 5 square roots of 5q over 7, minus 4 square roots of 3r over 7. Now you don't have to, but you could combine these into one term because they do have the same denominator. You could write it like that.
What's in the video just for that?
Let me get this off with the board up here.
Really, yours is really good.
Mine's all not.
Yeah.
No, it's not.
It's bad news too. You know, it's Friday afternoon and all Jay's teachers are putting his grades in. I love you, son. Just in case I die and he watches this video or something. My dad hated me.
I got proof.
All right. All right. So we are tasked with simplifying these radical expressions. What do you see immediately here? The second two terms can be added because they are like radical expression. So the first one is we're just going to kind of bring it down for now. 8m cubed plus 6 square roots of 2m. And don't be tempted to add those together.
Not tempted.
Okay. Now, is this simplified?
Yeah. No, well. Yes, it is.
Well, y'all are saying no because I asked the question.
No, it is simplified.
It's not simplified
Because of the 8.
because 8m cubed has perfect squares in it. So we have to be careful, right? 8m cubed, we could break it down into 4 times 2 times m squared times m. And these perfect squares get to come out, right? So we can take the perfect squares out, and when they come out, they multiply by the 3, so that'll be 6m times the square root of 2m plus 6 times the square root of 2m. Now, the question then becomes, can we do anything with those two things?
Yeah, you can add them because they're the same.
No, I don't think so.
But they're the same.
The inside parts are the same, but are the outside parts the same? So because we can't add the two. Now, we could factor it if we wanted to. We could take a square root of 2m out of both of those things and have 6m plus 6. But is that simplified? No, a simplified expression doesn't have parentheses, right? If you can multiply something, you have to do it. So we could have factored the expression by taking out a square root of 2m. But this is the simplified answer to this. Okay? All right? Try this one on your own. Okay, so what we would do is we need to simplify each of these individually, right? So 75 is 25 times 3. 27 is 9 times 3. Yeah, if I can get this to right. And c squared times c. So we can take out these perfect squares. And when they come out, they multiply by what's in front. So that will be, it is 5c times the square root of 3c because the 3 is left inside with the C. Sorry. Okay, and then the second term here, we can bring out the 9 as a 3, and that's a C, and then what's left inside is also a 3C.
Oh, there's a minus. I thought that was a plus.
And now we can, because the, oops, I left the C out of this one. Because the two radicals are like, and the outside terms are like, the outside parts are like, 5C minus 3C is 2C times the square root of 3C.
What you got?
That's probably not.
I heard somebody say squared, 3C squared.
Oh, no, I didn't say that. I got 3C.
Oh, okay. Square root of 3C. Okay, maybe that's what you said. You say 3C square root.
I might have.
Yeah, so 2C times the square root of 3C is what we get. All right? Last couple of these examples are quite easy. Find the perimeter of a right triangle if the lengths of the two legs are 4 square roots of 9 and 2 square roots of 64. And the hypotenuse is 2 times the square root of 100.
Okay.
They're all perfect squares, so this is really easily to simplify, right? The first side is 4 times 3, which is 12, plus 16, plus 20.
48. Wait, I want to write this
So the perimeter is 48.
down.
If you write anything down, Brooklyn, just write this. 4 square roots of 9 plus 2 square roots of 64 plus 2 square roots of 100.
Yeah, that's what I wrote.
So they're going to give you some expressions like this. Now, is that indeed, did they lie to us? Is 12, 16, 20 a Pythagorean triple?
I don't know.
Is 12 squared plus 16 squared equals 20 squared?
Yeah. Wait.
This is 144 plus 256, and that does equal 400. Okay. Just making sure they gave us a valid problem. You could tell right away that they are because they're in the ratio of 3 to 4 to 5. If you multiply that by 4, you get 12, 16, 20.
There you go.
Okay?
Oh, so like if you divide all this by 4, you get. I mean, if you divide all this by the numbers, you get 4.
Yeah.
Yeah.
That's what it's saying.
Is that what it's supposed to do?
Divide them all by what
like
number?
12 divided by 3 is 4, and 16 divided by 4 is 4, and 20 divided by 5 is 4.
Yeah. No, 20 divided by.
5.
Yeah, that's because, if you divide them all by 4, you get 3, 4, 5.
Yeah.
So what this is a 3, 4, 5 right triangle multiplied by 4, made 4 times larger. Okay, it's an enlargement of a 3, 4, 5 triangle. So every multiple of a 3, 4, every multiple of a Pythagorean triple is another Pythagorean triple.
Oh.
So if you multiply 12, 16, 20 by 2, you get 24, 32, 40. That's also a Pythagorean triple.
Did you do 1, 2, 3, and then
No,
all those ones?
because 1, 2, 3 isn't a Pythagorean triple.
Wasn't 6 and 10 one bad?
Yeah, 6, 8, 10 is 1. 3, 4, 5 has the distinction of being the smallest integral Pythagorean triple. And what we mean by integral is that it's integers.
Okay.
So that's the smallest integral Pythagorean triple. And you'll see a lot of, so you see 6, 8, 10 a lot on the ACT. You see 12, 16, 20 a lot on the ACT. Every multiple of this is a Pythagorean triple. The next smallest Pythagorean triple, 5, 12, 13. So every multiple of that is also a Pythagorean triple. All right? That's for free. That's good ACT fodder. All right? Now, this one tells us that the perimeter of the rectangular swimming pool has a length of square root of 800 and a width of 648. What is its, I know it's annoying, what is its perimeter? I'd just rather just practice adding these things and try to put it into some type of word problem that means something, right? Perimeter equals twice the length. Yeah, who measures anything like that? Plus twice the width. So what we're looking at here is 2 times the square root of 800 plus 2 times the square root of 648. Now, this is good practice to remind us how to simplify these things. What's the largest perfect square that divides 800? She said 400, and that's correct. Let's do it underneath like we've been doing, just to be consistent. This is 400 times 2. Now, hopefully the other one, if we divide it by 2, it'll also be a perfect square. What is that?
324.
324 is 18 squared, so we're good. All right. This is why it helps you to know the perfect squares up through 25. Well, really up through 20 and then 25. You don't really see 21, 22, and 23 and 24 a lot. You do see 24. 596, isn't that right? So anyway, you simplify these two now, and we get 40 square roots of 2 plus 36 square roots of 2.
Yes.
If you add those together, you get 76 square roots of 2 feet.
Who measures like that? No one. That's why it's ridiculous. Nerds. People that want to make life complicated.
In an attempt to make math relevant, we make it a mockery, right?
Yeah, like, I'm sorry, have you ever measured something like that before?
All right, there's your homework. Again, very important. Do not wait until Sunday late to do this. It's not going to do it this evening or do it in the morning.
I can't do it. I can't. I'll babysit my cousin.
I'll be here.
Yeah, because I have 2 sheets to go